All right, so homework this week. Chapter 3 homework quiz, so it's already up and ready to go. I think there's 2 attempts, just like all the other quizzes. So take one now, write down the questions you don't understand. There's also feedback after a lot of the questions, clues to help you solve the problem if you get it wrong. So make sure you do that by Sunday at midnight. And then there's also the discussion. So there's still quite a few students that aren't doing the discussions. Those are due every Sunday. I know they are not specifically written for every week on the schedule, but at the very top of the schedule it says discussions due every week. So make sure you're doing those. It's 10% of your grade overall. So if you don't do any of them for the whole semester, you're at a B, just with that. So, all right, now let's look at the problems. So chapter 3, all about motion, all about Newton. On Monday's class we talked about Newton's 3 laws of motion and then did some problems with force. So we're still doing force, we're just doing a different type of force now. So the force that we're going to look at now is centripetal force. So what centripetal force is, if you've watched the PowerPoints, or if you haven't, centripetal force is the force needed to go around a curve or in a circle. Okay, so anytime, say you're driving and you get to one of those roundabouts, in order to go in a circular motion, to go around that roundabout, you need a centripetal force. So when we looked at force before, when we looked at linear force, for example, our equation was F is equal to ma. So now with centripetal force, if you look at your equations, let me get my equation sheet out. I think I gave you the wrong equation sheet. Did I give you chapter 4? Chapter 3. Oh, no, I did read it right now. Okay. So I'm looking at centripetal force and acceleration. Notice there's a couple different equations under that heading. So this original force equation just changes where we put a C here, so centripetal force, mass times, and then A sub C. So centripetal force, centripetal acceleration. So that's one of the possible equations when we're approaching a centripetal force problem. Sometimes the acceleration is not given to you. So in that case, you would have to look at the next force equation, which is mv squared over r. So for this one, m is mass, v is velocity, and r is a new one. So r is actually the radius. So when we're talking about centripetal force, I just said it's a movement or motion in a circle. So if you think about a circle, the diameter of a circle is all the way across. This would be d for diameter. So what the radius is half of the diameter, half of the circle. So in the problems that we'll see, when you need to use this equation, they'll either give you the diameter, and if they give you the diameter, what you're going to have to do is divide that by 2 to get the radius. Because diameter equals half the radius. Other times, they will just give you the radius of the circle, and you can plug that in. And we'll look at both types of problems. I just wanted to explain what this variable is, since we haven't seen it yet with all our other equations. All right, so let's look at this centripetal force problem and use the equations we have to solve. So we write one more equation here. A sub c, so centripetal acceleration is v squared over r. So notice this v squared over r is this portion, AC, in that equation. So we really just plugged this in for where AC was. All right, now I have all my centripetal force and centripetal acceleration equations. So let's read this, approach it, write our knowns and unknowns, and then pick what equation is going to be useful to us. So we have an ATV with a mass of 230 kilograms. So for my knowns and unknowns, my first piece of information is that 230. We just said that's a mass. So the symbol for mass, the variable is m. So m is equal to 230. It takes a curve. So the fact that it takes a curve, that it's going in a circular motion, we know it's centripetal. Okay, it also tells us specifically at the end that it's a centripetal problem. So it takes a curve with a radius of 18 meters. So it's giving us the radius this time, the R value. Next piece of information, at a velocity of 31 miles per hour. So velocity would be variable v, and then 31 miles per hour. Got my knowns. Now what's the unknowns? What is it asking me to solve for? It's asking me to calculate the centripetal acceleration, so A sub c, and the centripetal force, F sub c. Before I pick equations to solve, I want to look at my knowns and make sure they're in the correct units, that I need them in. So mass, kilograms, that's good. Radius, which is a distance, a length, in meters. And we want all of our distances, our heights, our radiuses, everything we want in meters, so that's good. Velocity, we have it in miles per hour. We don't want it in miles per hour, so we do have to convert this one. We're going to convert it to meters per second. That's what we want our velocity in. So that's going to be my first step, and I'm going to do that off to the side over here. So, I'm converting 31 miles per hour to meters per second. To do that, I need a conversion factor. It's the same conversion factor that we used in Chapter 2 for our velocity problems, and that is 0.447 meters per second is equal to 1 mile per hour. So we start with my little plus sign. This 31 mph, that's what we're going to start with. That's what we're trying to convert. Then we take our conversion factor and put it here. I want the 1 mile per hour portion on the bottom so that miles per hour are on opposite sides of this horizontal line, thus canceling each other out. Then I will have my 0.447 meters per second on top. What does that get me? 31 times 0.447. Since this isn't my final answer, we're not worried about sig figs. This isn't an answer I'm reporting. So I'm just going to keep all the digits that my calculator gives me. And it says 13.857. What we did was multiply 31 times 0.447. Write it down here so it's not running into stuff. So I didn't worry about sig figs because it's just a number I'm using to solve my problem. It's not my final answer. So let me put that here. Okay. So everything now is in the units I want. So let's pick an equation. So if I wanted to solve for centripetal acceleration, well, the nice thing about that is there is only one equation for centripetal acceleration, so that narrowed it down for me. So I'm going to be using this bottom equation here. I'm going to plug in my velocity, making sure that I'm using the meters per second version. Square that number, and I'm dividing it by the radius, which is in meters. So now is when I'm going to want to worry about significant figures. So I look at the numbers that I used. This top number has a lot, so we're looking at the bottom number, the radius. So the radius only has 2 significant figures, so my answer should be in 2 significant figures. So when I calculate it out, I get 10.66 and a whole bunch of other numbers. So since I just said 2 significant figures, 1, 2, look at the number next to it. Is that going to stay a 0? No, we're going to round it up. So it's going to be 11, and the units on it are meters per second squared. Acceleration is always measured in meters per second squared in this course. So Now let's solve for our other unknown. We had two unknowns, so we're going to need two equations. So my centripetal force, I can actually use either of these. It doesn't matter. I have all the information I need to use either one. I'm going to pick the top one because there's just less to do, right? You only have to multiply one number by another number. Saves me some time and some trouble. So I'm going to use, using my new centripetal acceleration that I just solved for, centripetal force is equal to mass times centripetal acceleration. Plug in my mass of 230 kilograms. What's the weight of that ATV? And then multiply that by centripetal acceleration, we just said was 11. And this is going to give me how much force is required to get that ATV around a curve. 2530. So 2 sig figs. It's one of those weird ones. So it's going to stay at 5. That's our 2 sig figs. But we still need numbers here as placeholders. So we're going to put zeros for both of those numbers instead. Because that way they're not significant, but we're still in the 2000 range. So it is 2500, and the units, since it's a force, are newtons. So it doesn't matter if we're calculating linear force, gravitational force, weight force, centripetal force. Force is going to always be measured in newtons in this course. Also, I'm saying in this course. There's other ways to measure force. We're just focusing on a small subsection of that. All right. Questions on this one? Making sense? All right. So let's look at another one. Look how it takes the whole board for one problem. There's actually two parts to the problem, though. So if you saw a similar question on homework, that would have been two separate questions. I wouldn't ask you to solve for both in one question. I just like to combine them. Makes me having to write less questions on the board. All right. So now we have a fighter jet example. So these are questions straight out of, oops, that's a comma, the PowerPoints. I'm not going to write it word for word. I'm just going to kind of write the important parts. So it's accelerating 88.2 meters per second squared. Makes a turn. Radius 9.5 meters. We're going to calculate its velocity and the centripetal force. I took the words and wrote the symbols. All right. So let's start with our knowns and unknowns. Equation off to the side there. So we have, first piece of information is kilograms. What is that? So the units on it will tell me kilograms is a mass, so that's going to be my m value. They are accelerating at 88.2 meters per second squared. So that's not just my A, that's actually my A sub C. And you would know that based off of the fact that the jet's making a turn. It's going around a curve, circular motion, centripetal acceleration. So it's my A sub C. You can also tell by the units on that it's an acceleration, meters per second squared. Makes a turn with a radius of 925 meters, so R is going to be my 925. It wants you to calculate the velocity, which is V, so that's my unknown, question mark by that guy. And then it says centripetal force. So if you didn't know it was a centripetal problem already by the fact that they're making a turn and that they gave you a radius, you would have figured it out by the unknown itself. Centripetal force, F sub C. two unknowns, we're going to need two equations. Okay, and actually it doesn't matter which one we solve for first, but let's do the hard one first. Let's do velocity. So velocity, I have these two to choose from. These are the only two with velocity in it. Well, looking at this one, I have mass right here. I have the radius. I don't know the velocity, and I don't know the centripetal force. So I can't use this one because I have two unknowns. Looking down here, centripetal acceleration, yes, I have that. Velocity, that's what I'm trying to solve for. Radius, yes. So you just kind of go through and see which one can I use. And this is the only one that works because it's the only one that has one unknown, that being velocity. So I'm going to take this equation and rearrange it. Before I do that, let's just double check our units. Mass in kilograms, check. Acceleration, meters per second squared, that's good. Radius, meters, good. So we didn't have to convert this time, anything, any of the values. When we calculate velocity, the unit should be meters per second. So we're taking AC, v squared over r. So we're going to get v by itself. So rearrange. So r is in the denominator. So to get rid of it, I'm going to multiply by r. Whatever I do to one side of the equation, I have to do to the other. So by multiplying by r, I have r over r, so they cancel. So now my equation has AC times r is equal to v squared. I want v by itself, and it's squared. So how do I get rid of the squared? We did this before with the distance equation. You have to take the square root of it. Whatever I do to one side, I have to do to the other, so I'm going to take the square root of that side as well. So this cancels out that squared, so now I have v by itself. V is equal to the square root of the acceleration times the radius. So my rearranged equation, there, now I can plug in. So A sub c is 88.2. Radius is 925. So using those two numbers is how I'll figure out how many sig figs to report my answer in. So I have 3 sig figs, and then 3 sig figs there, so 3 in my answer, for an answer of 286. Quite a velocity, but it is a fighter jet, so it does make sense. Units on velocity, just said it a moment ago, meters per second. It's going 286 meters per second when it takes that turn. All right, now, centripetal force. Once again, I could use either. I have enough information. I'm going to choose the top one because it's simpler. So I'm going to simply take the mass times the centripetal acceleration. The mass of that fighter jet, 27,000 kilograms. Multiply that by the acceleration, 88.2. We're going to get a huge number, but our number should only have 2 sig figs. So you could report it in scientific notation to aid in that. Little practice from chapter 1. So 2, 3, 8, 1, 4, 0, 0. That's what I get. Remember, I said 2 sig figs. So counting from left to right, those are the only 2 that I want of actual non-zero numbers. Look to the number next to it. That 3 is going to go up, since that's a 5 or higher. So it's going to be 24. Now, all of these other places, I can't just cut off those numbers. I need to have zeros in each of those spots. So it's going to be 1, 2, 3, 4, 5 zeros after it. 1, 2, 3, 4, 5. So 2,400,000. It's a force, so it's newtons of force, which would make sense. It takes a lot more force to turn a jet fighter plane than it would a car, because they have more mass and they definitely have more acceleration. All right, so we solve for both? Yes. 2 million newtons, that's a lot. All right. So now, let's switch gears. So we've used all three of these equations. So let's look at gravitational force next. So it's the last set of force equations on your sheet. So right under centripetal force and acceleration, we have the gravitational force. Don't get that confused with weight force, because I know in the video on Monday, I accidentally labeled F of G for the weight force problems instead of F of W. I did change it, corrected it, told everybody in the video it should be corrected, but I make that mistake sometimes too, so just be very careful between weight force and gravitational force. They are different equations, they are different things. So, gravitational force is the force felt between all objects on Earth. These are very, very, very small forces. Okay, so we just saw a force of 2 million something, right? That's a huge force. What we're going to calculate with gravitational force, with F of G, are these tiny, tiny, minute forces. So, this equation here, what gravitational force is it's the force that you exert on all objects around you, and the force that all objects around you are actually exerting back on you. So like, I'm exerting a force on this calculator. I'm not touching it, but there is small gravitational force between us. So these forces depend upon the mass of the two objects involved. So that's why there's an M1 and an M2, because the gravitational force is between two different objects, so there will be two different masses, unless the objects happen to have the same mass, and that would just be coincidence. So it depends the mass of the objects, but it also depends how close they are. So this R, this is radius, just like we saw in the centripetal force. Okay, it's the distance between the centers of both masses. So the closer I am to an object, the more gravitational force I exert on that object. The further away I am, the less gravitational force I would exert on that object. Okay, so let's look at what types of problems, because I explained the concepts quite a bit in the PowerPoints, but I don't do any problems in the PowerPoint, so let's focus on that using this equation. So we have calculating the force of gravity between a person with a mass of 90 and a car. Realize the sig figs are going to be horrible on this one, so you only need one. That's okay. Their centers of mass. Okay. Writing too much. I'm already running out of ink tonight. Marker. So, calculate the force of gravity. Force of gravity is F of G. We got some hints already. Now it's saying between a person and a car, because I just said gravitational force was the force felt between two objects. So we have one of the objects being a person with a mass of 90, so that's going to be my M1, my first object. And then the car with a mass of 200 kilograms. So I have two masses, two objects, so I'm going to label him M2. Then it says their centers of mass between those two objects, between that person and that car, are 10 meters apart. So that 10 meters oftentimes when we see meters, we think distance, because that's how we started. That's the variable we started with when we did all of our velocity equations. But in this case, since it's the gravitational force equation, that value, that 10 meters, is R. Okay, so this is going to be my R value. Since it's meters, I know it's a distance and not a mass. So let's write these knowns and unknowns in a list, kind of keep track of them better. I have my M1, I said was the person, 90 kilograms. I have my M2, the mass of the second object, the car. And then I have my radius, so the distance between those two objects, 10 meters. And my unknown was the F of G, gravitational force. All right, so checking units. Mass is in kilograms, we're good there. The distance or radius is in meters, good there. When I calculate force, it should be in newtons. All right, so I said these were very, very tiny forces, so when we calculate it, it's going to be a very small number. Because you don't even feel the forces between you. When you walk up to a car, you don't feel a force unless it's in motion, right? So they're real forces, real enough to calculate, just not so much to feel. So using the only equation we have, M1, M2 over R squared. So notice the first variable is a G. I don't have a G in my list. Well, if you look at the equation sheet, you are given the G value. This is the gravitational constant, so this value remains the same for every calculation. So you need to plug in this number in scientific notation. Okay, so if I go over here, my G is 6.67 times 10 to the negative 11. So that's my G value. My M1 goes next, so I'm going to multiply by the mass of the person, 90 kilograms. Then my M2, the car, at 2,000. Then in the denominator, we put our radius, but remember, look, we square it. So it's going to be 10 squared. Enter all of that into your calculator to calculate the gravitational force. Really should just write down the answers for these so I don't have to calculate. All right. Now notice one sig thing. So depending how you have your calculator set up, it might give you the answer in scientific, or it might give you the answer in normal notation. So I'll write both. So I have 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6. And then 1. 1, 2, 3, 4, 5, 6, 7. So that would be 1 times 10 to negative 7. So these are the same answer. Just one is in normal notation, which we learned from chapter 1, and the other is in scientific notation. So both of those would be acceptable answers. Notice, very, very small number, very, very small force. That's why we don't feel it. Oh, I also posted a practice sheet with answers, a practice worksheet. So if you are having troubles on the quizzes at all, you can always try doing the practice worksheet first, checking your answers, and then if you're getting any wrong, try more of that problem, or even email me. We can set up a meeting. So, all right, let's try another one, same type of problem, okay? So, looking at the next one, now we have two cars parked close to each other. So we're going to calculate the gravitational force of those cars. What force are they exerting on each other? So we have two cars, both 2,000 kilograms each. parked close to each other with their centers of mass. .2 meters apart. And then the question states, calculate the force of gravity. So F of G is our unknown. I'll just write that here. F of G is what I'm solving for. So this guy. So we have car 1, 2,000 kilograms. Parks close to car 2, which also has a mass of 2,000 kilograms. So kilograms is a mass, I just said, right? That's our M. Since both cars have the same mass, our M1 and our M2 are going to both be 2,000 kilograms. The other piece of information, 6.2 M, that's meters. This is a distance, or in this case, for this equation, it's our R value. That's how far apart the centers of mass are. So 6.2. Looking at the units, I don't need to convert anything. So I'm going to keep as is. Okay. Now notice we have another known, and that is the gravitational constant. So make sure you're including this in your calculations. When we solve for F of G, it's the gravitational constant that we start with. That's 6.67 times 10 to the negative 11. We're going to multiply that by the mass of the first object, which is 2,000 kilograms. The second object, in this case, they happen to have the same mass, so another 2,000. Then in the denominator, our radius, 6.2. Make sure to square that. So these objects are much closer to each other. So we would expect this gravitational force to be higher than the last problem. Because the closer the objects, the higher the gravitational force. There also, masses are bigger than the last problem. And the larger the mass is, the higher the gravitational force. So masses and gravitational force are proportional to each other. If one goes up, the other goes up too. So I'm expecting a larger number than last time, but still, since its gravitational force is not going to be a huge number, just bigger than we saw in the previous problem. So second, 11. Calculator. When I talk and calculate at the same time, I usually make mistakes. So. There we go. Let's see. We have 0 point. And 1/6 again, correct? Yes. Units, since its force is newtons. So it is a larger number. We had a number that was times 10 to the negative 7th in the last problem, so this one is larger, by a whole magnitude actually. So, be able to use all of these equations to solve for any variable in the equation, but then also make sure you're watching those PowerPoints, because the exam is probably half concept, half problems. Okay, and the exam is actually going to be on chapters 2, 3, and 4. So we still have one more chapter before the exam. And the reason they're all together is because they flow together. I mean, we talked about Galileo with velocity and acceleration in chapter 2. Now we're talking about Newton with force, and force has acceleration in it. So that's how that ties in. It also has velocities tied into it. And then next we're going to be taking force and talking about impulse and conservation of momentum, a whole bunch of things along that line. So chapter 6 is a lot longer than these last two chapters, so it's going to take a little longer than a week to get through it. So you'll actually have 2 quizzes for chapter 6, or chapter 6, sorry. It was chapter 6 last semester. We changed the order, so sorry, I keep messing it up. It's chapter 4 this semester. So you will have 2 quizzes for chapter 4. You only have 1 on this stuff, and it is due on Sunday by midnight. Don't forget the discussion. All right.